All right, welcome to our second part of the descriptive statistics lecture. This is on measures of variability, and then at the end we'll do a little bit with some related concepts, just two quick things. All right, so what is variability? Whereas central tendency speaks to where most of the scores fall, the center of the distribution, variability is thinking about how spread out the scores are. So, in other words, it has to do with dispersion, the spread, or the distance between scores. So if I were to say some people did really well on the test and some people did really poorly, that would suggest a lot of variability. In contrast, if I were to say my tips are always about the same, between $30 and $35, that would be small variability because the scores don't vary much around the mean there. And then third case, some students study only a few minutes a day, some put in 30 hours per week. That's an example of a lot of variability. Okay. The simplest measure we could come up with for a measure of variability would be the range. And the range works great for the weather, typically because the weather starts off cooler, it reaches a high temperature for the day, and then it cools down at night. So with that pattern, the range is a sufficient measure of variability. The problems, however, is there's just two scores that you're using. So it's not particularly good at summarizing a more complex or variable distribution, and it's unduly affected by extreme scores. So we need a better measure of variability, but if you just want a simple hand calculation for thinking about what variability means, the range, just the spread between the observed scores, that's a good place to start. Okay, so the big daddy that we're going to calculate is standard deviation. And the way I'd encourage you to think about standard deviation is thinking about the word standard as meaning the typical. So one way of saying it is the typical deviation of a score from the mean of the distribution. You could think about it as, this is technically you run into problems, but conceptually it's kind of like the average deviation of a score, how far a typical score falls from the mean. So most scores, once you define a standard deviation, it's helpful because you can then know mathematically, because of the way the normal distribution works, that most scores, in other words 68% of the scores, just about 2/3, are going to fall between +1 and -1 standard deviations. So we've calculated before, stop right there for a second. So at the end of the lecture, we're going to talk about a confidence interval, and that's that 68% range, and we're also going to relate that to the graph that we've already done, error bars, but that's going to come here just in a minute. Okay, so but first we need to build up this concept of standard deviation, and we're going to conceptually build it in 4 steps, starting with the concept of deviation scores and going from there. But I want to show you this is the formula that we're going to ultimately work up to. Read this as sum of x squared minus sum of x quantity squared, that part divided by n, and all of it, all this divided by n minus 1, and then square root of all that. All right, step 1, deviation scores. So here's the basic idea. You're going to calculate the deviation of every score and add it up. What do we mean by deviation? We're talking here about the distance a given score falls from the mean. So the formula for that, as simple as it is, would be x minus x bar. So for example, imagine that someone took a history test where the average was 80, and they scored a 90. So 90 would be the x minus 80, the sample mean. They would have a positive deviation score of 10. On the other hand, let's say somebody took a test, the average score was 50, heaven forbid, and they got a 40 on it. They did even worse than that. Then it would be 40 here. 40 minus 50 would be negative 10. So just a quick conceptual check here. If you do have a negative deviation score, you know that means that score falls where relative to the mean. So you can stop and think about that for a second. Does it fall to the left or the right of the mean? it would fall to the left because it's below average, so it would produce a negative deviation score. Okay, so maybe we could just add up those deviation scores, but there's a problem. Why can't we just add the deviation scores? Because they're always going to add to 0. This is one of those goofy math things. So just look here. If I have a score in the sample mean, 1 minus 2 would be negative 1. 2 minus 2 would be 0, and 3 minus 2 would be positive 1. I add those up. No! It's 0. So that's not going to work, because if we want to be able to characterize how much variability there is in a distribution, if no matter what happens, they always add up to 0, we can't show that one distribution has less variability than another. Everything's going to get the same measure. So we need to figure out some way of dealing with this canceling out to 0 problem. So what statisticians have come up with is this. It's called sum of squares. So their way out of adding up to 0 is to square every score. That way the negatives don't balance out the positives. So what we're going to do, and you'll see this mathematically, you'll square all the deviation scores and then add them up. And so technically what this is giving us is the sum of the square deviation scores. Statisticians, being lazy ne'er-do-wells, they just refer to this as sum of squares. So conceptually, what are we talking about? It's going to be a deviation score. There's the deviation score, x minus x bar. You square each one of those, and then you add them all up. So conceptually, this is how we think about it. Now, it turns out, for pragmatic reasons, we actually calculate it slightly differently. So through the magic of algebra, we can transform this into this. I'm not going to show you that, but you can do that on your own time some Friday night when you're bored, and show that these two are equivalent. So this is, you're going to see where knowing what sum of x squared is versus sum of x quantity squared is. That's why knowing that conceptual difference is important, why we did that little lecture before on that math review. So anyway, so how we think about it computationally, how we actually crunch the numbers. So, and make sure you keep these two straight, what's what. Unfortunately, we still have a problem. The problem is, now we don't have everything adding to 0, but what's going to be happening is larger samples, just because they have more numbers, are going to be generating larger sums of squares. So we somehow need to control for the size of the sample in representing how much variability it has. So we're going to go on from sum of squares to calculate this thing called variance. And variance, it sounds like variability, but variance is a specific mathematical construct. It has a specific meaning that's different than the broader concept of variability. So sum of squares, it's biased based on the sample size, and what we can do then is control for that by dividing by n. So all we do is take the sum of squares and divide by n. So one way of thinking about variance then is it's the average of the sum of the square deviation scores. Think about that for a second. You got the sum of the square deviation scores. When you divide a sum by an n, that gives you an average. Okay, so here's our formula. So written out longhand, we have here the sum of squares formula, and then to get variance, we simply divide by n. I can write this in shorthand by just saying SS, and this SS is equal to all this stuff on the top. I can just write SS is divided by n. And what those equal is variance. So this is variance because it has this 2 here, and this symbol, sigma, lowercase sigma, is the Greek symbol for variability. So this is saying that the variance, because it's squared, for a distribution of scores represented by x would be equal to this, all this nonsense. Okay, but we have one thing left to fix. Remember how we squared all those original deviation scores? We want to get back to the original metric. So here's what we're going to do. To get standard deviation, the final step, we're going to take the square root of the variance. So if you want to express things in the same metric as the raw scores, as in the same scaling system, then you're going to take the square root of the variance. And just a note here, the x subscript is optional. It'll become important later on, but if you're just dealing with standard deviation in one distribution, you can write it without writing that x. Okay, so here we have the formula written out, and you'll notice, contrast it back to the previous page, the only difference is that 2 drops away, and we get the square root. So the 2 drops away because it's no longer squared, so that's the way the symbol system works here. And now we have the square root of all this. So watch this. This is sum of squares, all this nonsense. Could be abbreviated like this. And then by dividing by n, you get this thing called variance. And to get back to the original metric, to get to the full measure of standard deviation, we take the square root of all that. So that's it. That's the 4th step. Okay, so let's work through an example. Let's say you graduate and all your dreams come true and you become chief bridge builder for the state of South Carolina. And your mission is to decide how tall to build the bridges based on the size of the trucks on the road. So I just made up some weird numbers here, so just bear with me. But let's assume that the trucks are these different heights that you take a sample of. 7, 6, 8, 5, 6, 5, 6, 7. So you've measured trucks, and that's how many units high they are. That's an average of 6.25. So can we just build the height of the bridges as 6.25? No, because that's the average. So half of the trucks, if the distribution is normal, are going to be taller than 6.25. So we need to accommodate that variability. So that's right, we need to calculate standard deviation. Surprise! So here's a calculation tip when you're doing this. You want to think anal retentive. So do it the same way each time and keep it neat and well labeled. Many times when students make errors on this, it's just because they get sloppy in their handwriting. Okay, so here we have a set of scores, 7, 6, 8, 5, 6, 5, 6, 7, these scores here. The first thing I need to do is write those in an x column, and then I have another column, which is x squared, where I square each of those. 7 times 7 is 49, 6 times 6 is 36, 8 times 8 is 64, yada, yada, yada. So 2 vertical columns, and then I can generate my summing statistics. So on the left here, if I add up all these x's, I'm going to get a sum of 50. So I have sigma x equals 50. This is capital sigma that kind of looks like an E. X is equal to 50. And then when I want to get my sum of x quantity squared, I just take that 50, multiply it by self, and that comes up to 2,500. Over here, with the x squared column, I need to calculate, need to add up all those, and that gives me sum of x squared. So sum of x quantity squared, sum of x squared. And then lastly, you need to note how many observations you have, which we have 8. So these numbers here that I've circled in red, the sum of x squared, which is 320, the sum of x quantity squared, which is 2,500, and n, the number of observations, is 8. We're going to pull those numbers into the formula now. So hang on, we're going to the next page. So here's the formula. I have, this is sigma x and then the whole standard deviation formula, and I'm going to plug in. For sum of x squared, I'm going to plug in 320. For sum of x quantity squared, I'm going to plug in 2,500. And then for n, I'm going to plug in 8. And then I got another n down here, I'm going to plug in 8. So this stuff on the top is going to resolve to 7.5, and the n is going to just be 8 on the bottom. So I get 7.5 divided by 8 is going to be the square root of 0.9375. I take the square root of that, and I get the standard deviation is 0.9682. So it's just about equal to 1. So quick computational note here. Remember your order of operations when you're calculating this. So this has to be 2,500 divided by 8 and then subtract it from 320. If you go 320 minus 2500 and hit enter and then divide by 8, you're going to get the wrong answer. Do the division first, then subtract it from the first number. Okay, so where are we? So we found the standard deviation is equal to 0.9682. So putting that back in context, we'd expect the truck height to range somewhere around 6.25, and one easy way of capturing 68% of the scores would just be to take that mean plus or minus the standard deviation. That gives us a confidence interval of where the truck heights are going to fall. So in other words, they're going to fall, this range we've calculated runs from 5.25 to 7.25. Again, that's the mean plus or minus the standard deviation of 0.9682. And notice I've done a little bit of rounding here just to make it easy. Okay, but now we need to go in the last major step here in getting this calculation. Recognize that if we're trying to build bridges for all the possible trucks in South Carolina, we had a sample that was just based on 8 trucks. So it's conceivable, in fact, it's almost positive, almost for sure, that we've missed some of the more extreme truck heights. So if we're going to calculate that standard deviation as an estimate of the full population and assume that what we had isn't a full population, then we have to make an adjustment. To calculate standard deviation as a population parameter estimate, we have to make this little adjustment here with n minus 1. So almost always, 99-point-something% of the time, you should assume that you're working with the sample and you're trying to generalize to the population. So remember, a sample is just what you hold in your hand, the scores you actually looked at or actually measured, and then the population is all the potential scores out there. So to correct for this, mathematically it works out. This is a little wild, but this is how it works. If you just divide by, instead of n minus 1, that's just enough of an adjustment that then this becomes what's called an unbiased estimator. In other words, it's going to more accurately represent the true variability in the population. So here's the way to think about it. If you're hungry and you're walking to dinner and you're with 4 friends and you say you only have, say your mother is giving you $20 to buy some pizza, and you say, I'm really hungry, so I'm going to push one of my friends off the bridge, and then there's only 3 of us, and that way my share of the pizza is going to get bigger. So in other words, if you have a certain size pizza and instead of dividing it by 4, you divide it by 3, each of those slices get bigger. So in the same way, dividing here by n minus 1, it's going to bump up this measure of variability just slightly. So let's see what that looks like in terms of our example. So here we have the formula, and you'll notice there's a slight change from the original formula. We got this n minus 1 thing going on, and because of that, we now will recognize this as a population estimate. So we're not using that Greek symbol, we're using just lowercase s. By the way, the little hat is just to make sure you understand it's a lowercase s, because a capital S means something else. But for our purposes, it's not crucial to have that notation. Okay, so again, you'll notice I plug in the same numbers, the 320, the 2500, the 8, because on the top I still have sum of x squared minus sum of x, quantity squared divided by n, that's sum of squares. But now, instead of dividing by n, or 8, I divide by n minus 1, or 8 minus 1. So you'll see here, this resolves to 7.5 divided by 8 minus 1, which works out to the square root of 1.0714. And when I get that, my standard deviation now is 1.0351. And you'll notice that compared to before, there is the standard deviation now is slightly larger than the standard deviation we calculated initially. So initially, we assumed we had all the scores we cared about. So we calculated a population parameter. But down here we said, no, we don't have all the scores we care about. So instead we calculate standard deviation as a population estimate, and you'll notice it's a little bit bigger because we assumed we missed some of the extreme scores, so we should bump it up a little bit. So standard deviation as a population estimate is always larger. Okay, so we get standard deviation then in a variety of different forms. And if you look on your quiz vocabulary sheet, you'll see that it's broken down like this. And this is down here in this lower right hand corner. This is the main one where I have that standard formula. And this is standard deviation as a population parameter. Conceptually, you should also know what's going on with the other ones. So if you look here on this side, on the right hand side of this table, we have these are all dealing with standard deviation. And the only difference is this formula on top is standard deviation as a population parameter, and this one on the bottom is standard deviation as a population estimate. If I move over to the left, for each of these, there's the corresponding formula for variance, which is just like standard deviation, except without the square root. So you should be able to know each of these formulas and should be able to calculate things based on them. So I might say calculate the variance as a population parameter, calculate variance as a population estimate, whatever, and you should know what to do. In the real world, this is the formula, the standard deviation as a population estimate that you're going to use most of the time. Okay, so students always want to know, when do I use standard deviation as a population estimate, the sigma x versus the s minus 1? Well, you should always assume that you have a sample and you're trying to estimate the population, unless I tell you something specifically otherwise. So, for example, if you are told that you have all the scores in the population, like say you have all the SAT scores because you're the company that designs the SAT, or the other classic example is you're norming a scale. In other words, you're trying to create the index of where normal people perform on your scale, like on a scale of anxiety, say. And if you do that, you have a very large sample to work with. In both of those cases, you can go ahead and assume you're working with a population parameter. Functionally, just mathematically what happens is if you're working with a large sample, even just say 30 and above, the difference between n minus 1 and n gets to be pretty paltry. So, but you should think in terms of this being your home base, using that, the standard deviation as a population estimate, the S, using the n minus 1. That's what we use unless you're explicitly told to do something else. Okay, so let's practice. Got two practice problems here for you. So if I give you this problem, calculate there, I'm explicitly telling you to calculate standard deviation as a population parameter. Calculate the standard deviation for these three numbers, 4, 2, and 3. So that's a really small distribution. It's small just because I don't want to have to make you use a lot of numbers to start with here. Okay, so what's this look like? So you should know that first you're going to list the vertical a vertical column with those x values, and then right next to it you should figure out x squared. So go ahead and hit pause and see if you can set that problem up initially and go ahead and get the sum of x squared, the sum of x quantity squared, and the and to note what n is. Okay, so I'm hoping what you did was write down 4, 2, 3, and then right next to it figure out the squared values, 16, 4, and 9, and then you can get the summative values. So for x, if I sum up 4, 2, and 3, just the x values, I get 9. That's sum of x is equal to 9. If I want to get sum of x quantity squared, this next value right below it, then I just square that, and that's 81. Over here on the right, to get sum of x squared, I'm just going to add up the squared values of x and get 29. Okay, so once I got those values, I can write down my formula, and again, I'd always write that out, but you can write out the formula for standard deviation as a population parameter, and then plug in stuff. So for here, for sum of x squared, we're going to plug in that 29 minus sum of x quantity squared, which is 81, divided by the n, which is 3, and so it'll look like this. And then if you resolve that, it'll work out to sum of x is equal to 0.8165. Okay, so let's try the next one. So now I'm telling you to calculate standard deviation for 3, 2, 1, and 1. Now, I haven't told you what formula to use, so you should assume that you're calculating standard deviation is a population estimate, in other words, the S. So there are the numbers 3, 2, 1, 1. Go ahead and work and see if you can get the correct values for sum of x and sum of x squared. Excuse me, sum of x squared, and sum of x quantity squared. And you can hit pause while you do that. Okay, so we should have gotten the x squared values here of 9, 4, 1, and 1. And then in that x column, I should 3, 2, 1, and 1 will add up to 7. And then if I square that value, I get sum of x quantity squared, which is 49. And over here, if I add up the x squared values, I get 9, 4, 1, and 1, and that adds up to 15. So I got sum of x squared is equal to 15. And you'll note I just went ahead and calculated the average. It's just these values divided by 4, and I've noted here that the n is equal to 4. Okay, so go ahead and hit pause, and I want you to get the right formula written down and plug in the values and solve for the S value, the standard deviation. You can hit pause. All right, so you should have gotten the standard deviation with the n-1 formula. Plugging in on the top in the sum of squares part, you're going to get 15 minus 49 divided by 4. And then below that, you're going to get n-1, which is 4 minus 1, which should resolve to 2.75 divided by 3. The square root of all that is 0.9574. Okay, that's standard deviation. And we have more practice problems, of course, in your notebook. Let's hit just 2 more things, and then we'll be finished with this part of the descriptive statistics lecture. So, confidence intervals. A confidence interval combines the mean with standard deviation. So now that you have those 2 tools to work with, we can combine them and get another tool. So this is read as a 68% confidence interval is equal to the mean plus or minus 1 standard deviation. So conceptually what that means is if I take the mean and add and subtract a standard deviation from it, I've defined then a range in which 68% of the scores should fall. So I can be, another way of saying that is I can, with 68% certainty, predict that a given score in that distribution is going to fall within that range. So what would that look like with real numbers? Let's turn to Bob and his history test. So Bob took the history test after the rest of the class. The class scored 70 on average with a standard deviation of 10. So assuming Bob would be scoring normally on that test as any other student, what would you expect Bob to get? In other words, how could we calculate a 68% confidence interval? Well, we'd want to take the mean and add and subtract 1 standard deviation from it. So hit pause for a second here and see if you can figure out what that would be. Okay, so what you should have plugged in is 70 plus or minus 10, because 10 is what is 1 standard deviation. And then you're going to get 68% confidence interval is equal to the range between 60, 80. So this 60, 80 means 60 to 80 is the confidence interval. So in other words, we'd expect Bob to get between 60 and 80. And if we made that prediction, in the long run, over multiple attempts, we'd be right about 68% of the time, assuming the distribution is normally distributed and that Bob didn't cheat or call his mother and ask for the answers. Okay. Last is thinking about SPSS and the error bars that we've calculated before. So error bars are just a way of taking descriptive statistics, like I've represented here, and I'm using the data from the truck height example. works out that the mean was 6.25. Remember, we calculated the standard deviation is 1.035, and this in SPSS it's always giving you standard deviation as a population estimate. So if we wanted to represent that graphically, in essence we want to take that mean plus or minus 1 standard deviation, and so what you get is this error bar here, right, where if you ask and specify in the dialog box setting it up, you get the mean plus or minus 1 standard deviation. So you see the mean is centered on 6.5. That's why the little circle there is in the middle. And 6.5 goes up to a little, almost 7.5, and then it goes down to roughly 5.5, showing you that range for that standard deviation. So again, just here graphically, the distance between the mean and the edge here, that's equal to 1.035 is the variability we're dealing with. Okay, that is it. So thanks for your attention, and we will move on.